Hello Noddies, welcome back to the channel. In the previous videos, we explored about the LC low pass filter and high pass filters. Today we are going to take that idea one step further. We will investigate whether an LC low pass filter can behave as an integrator and whether a LC high pass filter can behave as a differentiator. We will derive the transfer functions, understand why these circuits perform double integration and double differentiation, simulate them in cadence, and finally see why practical implementations don't always behave as expected. So let's get started. Here, let's begin with the LC low pass filter. We already know low pass filter passes only low frequency signals and attenuate higher frequency. And for integrator, we have to basically design a low pass filter and give high frequency signal as input. Here, the transfer function is given as this. For a perfect integrator, the transfer function as h of s is equal to 1 by s. However, our low pass filter doesn't contain a single power of s in the denominator. Instead, at sufficiently higher frequencies, it has h of s is equal to 1 by s square, which is actually a double integration. So we can expect the VO to be double integration of the input signal. Now let's look at the LC differentiator. So to basically design a differentiator, we are basically designing a high pass filter and giving low frequency as input to it. For a circuit to act as differentiator, we have to have the h of s term as s. But so from our transfer function, we can see the h of term is equal to s square. So which means the double differentiation. So here we can expect the double differentiation of the input at the output. Now this may raise a question. What's the difference between the S and H square? For example, let's take we are giving a RAM signal as the input. We can expect step input as the output if the transfer function is S. But since the transfer function is S square, if we try to give a RAM signal as the input, we will get direct impulse at the output instead of getting the intermediate step signal. So this is the difference between the double differentiation. And for the double integration, if we try to give an impulse as the input, we can directly expect the ramp at the output instead of seeing the intermediate step signal. At this point, we might think, great, we have a double integrator and double differentiator. Why not use them directly? The answer lies in the resonance. Both circuits contain an inductor and a capacitor, so at resonant frequency omega is equal to 1 by root of LC. The LC pair mostly behaves like a resonator, a tank circuit, or an oscillator. The energy continuously exchanges between the electric field of the capacitor and the magnetic field of the inductor. As a result, the circuit becomes highly oscillatory. Instead of producing a clean differentiation or integration output, it starts behaving more like a resonator. Now let's verify this through a design and simulation. Before we continue, if you haven't watched the previous video on LC filter design, click the I button on the top right corner. In that video, we discussed an important practical question. Why do we choose millihenry inductor instead of nanohenry inductors for low frequency designs? That discussion will help this example makes much more sense. So now let's try to design a differentiator. As I said in the previous slide, if I try to give a ramp signal as the input, we should get the impulse at the output. So let's assume the cutoff frequency to be 10 kilohertz and the inductance to be 10 millihenry. So this is basically a high pass filter and I am going to give a low frequency of around 100 Hz as the input. Here we get the time period as 10 millisecond, which is nothing but 1 by Fn. So we know that the formula for cutoff frequency is equal to 1 by 2 by root of LC, and by substituting these values I get the capacitance to be around 25.3 nanofarad. So this is our expected graph. If I try to give an RAM signal, I should see a spike, which is the impulse signal at the output. Now let's try to simulate this in Cadence and verify whether we are getting our expected graph. Open your Cadence, press I to go to the add instance window. Here find your inductor, and inductor is found to be 10 millihenry. Place your inductor. Press I again to go to add instance window. Here find your capacitor, and our capacitor is found to be 25.3 nanofarad. Press R to rotate your capacitor. Place your capacitor. Press I to go to the add instance window. Here find your V pulse. Here give your voltage to S1 and your pulse as 10 millisecond. And in order to get the ramp signal, here give your rise time and fall time as same as your period. So I'm just giving 10 millisecond here and here. Place your V pulse. Press I to go again to this add instance window. Find your ground. Place your ground. Press W to finish firing your circuits. Check and save. Launch ADL. Choose your analysis as strands and give your stop time as 10 m. so that we can see 10 times of the input signal and the output signal. Here, choose your nodes, the input node and the output node. Press escape, run your simulation. So let me zoom it a bit. Here, instead of seeing a spike, we are seeing some oscillations, right? So this is not something that we want. So let's try to analyze why this is happening. Based on our theoretical analysis, we expected the differentiator to produce sharp spikes whenever the slope of the input changes. And this is the ideal response that is shown on the left. However, after simulation, the actual response looks very different. Instead of a clean spike, we observe oscillations at the output. So why does this happen? The answer is resonance. Near the resonant frequency, the inductor and capacitor continuously exchange energy between them. This stored energy causes ringing in the output waveform. As a result, the circuit behaves more like a resonator than an ideal differentiator. So how do we reduce this ringing? We introduce damping. The simple method to introduce damping is by adding a resistor. Once a resistor is added, some of the stored energy is dissipated, so the quality factor becomes 1 by R root of L by C. Here we can notice something. As the resistance increase, the quality factor decrease. A low quality factor means less resonance and less ringing. As a result, the waveform starts resembling the expected differentiator response much more closely. So now let's try to simulate this. Open your cadence, delete this node and find a resistor. And let's keep the resistance to be 1 kilo ohm here. Rotate your resistor by clicking R and place your resistor. Press W to finish wiring your circuits. Check and save. Go to the same ADL window. Here set your outputs as input and output. Press escape in your keyboard. Now run your simulation. From this simulation, we can actually infer that for every change in the ramp input, we can see the spike at the output. Hence, we got our double differentiator output. Here, we tend to got our expected output. So, Noddies, in today's video, we learned that LC low pass filter and high pass filter can approximate integration and differentiation, but not in the way that many people expect. Instead of behaving like 1 by S and S, they behave like 1 by S square and S square, which means double differentiation and double integration. We also discovered why resonance prevents the circuits from behaving like ideal mathematical operators and how adding damping helps control the oscillations. We'll see you in another interesting video. Until then, keep learning, keep simulating, and keep building.